else we'll see if we can wrap it up in the session itself. So basically the ideal op-amp is a 5-terminal device, but we have drawn it using 3 terminals, and the 2 input terminals are labeled 1 and 2, and the output terminal is terminal number 3. The ideal op-amp has an open loop gain which is infinity, and practically it can be a huge number as much as 200,000 or more, and it's called a difference amplifier because the output is the amplified version of the difference of its inputs. So let's see if I can get this to right. V out is A times V2, because that's the positive terminal, minus V1 in the open loop configuration. And if A is like about 200,000, then it's a very high amplification and it saturates quickly. So when we say that the amplifier has the ability to amplify by such a large amount, it means that the power to amplify is coming from some source, and those are the power sources used to bias the circuit. So that is VCC and minus VEE, reminiscent of the symbols we used in the BJT. The terminal 1 is called the inverting terminal and 2 is the non-inverting terminal. And the reason for that is the output is V2 minus V1. That is the voltage applied at 2 minus the voltage at 1. If you were to look at the transfer characteristics, then if the input voltage, when we write Vi, that refers to V2 minus V1. So the difference of V2 minus V1 is the net input voltage Vi. If that's applied at the input terminals, then the voltage transfer characteristics shows a slope which is linear and a slope of magnitude A, where A is the gain of the op-amp. This is the open loop configuration. That means there is no feedback path over here. It's just the 2 inputs and 1 output. And what you notice is that although the gain is very high, it does not mean the device can infinitely amplify the signal. It will amplify it until a maximum value, which will correspond to the values that are supplied by the power supply. So if I have VCC volts here, then the maximum output voltage can be VCC. And in the negative side, if it's minus VEE, then the maximum negative voltage is minus VEE over here. The slope as drawn in this figure is very, it's amplified greatly, it's exaggerated, that's the word I was looking for. So it's highly exaggerated. And in reality, what would happen is this would be a very sharp line, so that it would almost look like the input and output characteristic would almost look like it's right on the axis like this. So that's because the difference, the Vi value where amplification is happening is a very tiny amount. It's like a few microvolts, few tens of microvolts. So for exaggeration, we have drawn a large slope, but in reality, it will be very sharp. The circuits that we analyzed last time use some rules, which we called as the ideal characteristics. The ideal characteristics of the op-amp were that it has infinite input impedance and 0 output impedance. This is what we desire in any amplifier circuit. High input impedance, so that any signal voltage which is applied will fall at the input, and any output which is taken out from the amplifier will go entirely to the next stage without having any voltage drop over here. We said it has 0 common mode gain. That means if the inputs 1 and 2 are equal, then the output should be 0. And we said infinite open loop gain A, and that we have here as a very large number, and infinite bandwidth. And this is not something we are touching this semester. This is mainly got to do with the frequency response. We may briefly hint at it, but we'll not go into detail. Now, the fact that the op-amp has such a steep characteristic makes it what is known as a comparator. A comparator is basically a device which compares 2 inputs. So it tells you if input 1 is higher than 2 or is 2 higher than 1. Since we know that the op-amp IV characteristics or the op-amp output voltage is given by A times the difference of 2 inputs, V2 minus V1. Let me make this 1, not I. Then the way the comparator works is if V2 is greater than V1, then the output will go to a positive value. It will saturate at a positive value because the moment the input is even slightly above the output. So even if the input were, say, let's say V2 is 10 microvolts more than V1, then 200,000 times 10 is like 2 million. So that's like 2 volts, right? So if the input is 10 microvolt, that is delta V. V2 minus V1 is 10 microvolt. Then A times delta V is 10 into 10 to the minus 6 volts into 2 into 10 to the 5. So that's 2 volts. That means even if there's a very tiny difference of 10 microvolts at the input, the output quickly becomes in the magnitude of volts. So it can quickly go to saturation. Similarly, if the input is a negative value, that is, if V1 is greater than V2, then you will quickly go to the negative saturation value. So how would this work? Supposing we have the input being a waveform that looks like this. Let's say it's a sinusoidal signal, and let's say the sinusoids have varying magnitude. What will the output look like for this case? If I use a comparator, which means it's an op-amp with an open loop configuration, right? So which has typically infinite gain. So then the way you would do it is to find out all the zero crossing points. You know that the common mode gain is 0. That means when the two inputs are equal. So when I say that this is the input axis, what this reflects is actually it is V2 minus V1. That's the input, right? So for example, I need to pause for a second. Yeah, I had to pause because of the internet issue and the Zoom stopped recording. So where was I? Yeah. So if the input 1 is at ground and then the signal is applied to input 2, which what was the signal I drew over here, the big one, and then so then this comparator input is V2 minus V1. Since V1 is equal to ground, it's basically tracking V2. If V1 is say 1 volt, is some positive value, then I would have to take V2 minus V1 and there would be a level shifting over there. So now let's assume this is V2 minus V1. What is the output of the comparator? We know that because in the open loop, there is very high gain. So the device always goes to saturation value. So whenever there is a positive signal, it will go to a positive saturation value. Whenever there is a negative signal, negative saturation value. The amount, it does not depend on the magnitude of the input. As long as the input is above some threshold, then the output will automatically go to saturation. So whenever there is a positive slope, it's this. Whenever there is a not slope, positive region, it's this. Whenever there is a negative region, it's this. So it's saturating from some positive value to some negative value. This will be plus VCC minus VEE. This is the V out. That means the op-amp as a comparator can be used as a square wave generator. Now, based on the open loop configuration, we discussed how it basically behaves as a comparator or as a zero crossing detector. Whenever you cross a zero value, it can detect whether you're in a positive side or a negative side. But then when we wanted to actually use it practically, we decided that we needed to give feedback to the system. And let's see how this feedback works. So there are a couple of golden rules for feedback. That is, one is the output attempts to do whatever is necessary to make the voltage difference between the input zero. That's a mouthful. What it means is we use this rule of virtual ground. We said whatever is the voltage at terminal 2 is the same thing that's reflected at terminal 1. That's actually this rule which is being adhered to. What happens is the output changes its value through this feedback path so that the difference between the voltages 1 and 2 become almost 0. The way to analyze this is, let's assume initially there was no feedback resistor R2. So if there were no feedback path R2, then the terminal 2 is grounded and the input voltage is the input signal is given to terminal 1. What you expect is exactly what we saw in the previous slide. That means if the input voltage, in this case it's kind of reversed, if terminal 2 is grounded and terminal 1 is the input voltage, then whenever I have this waveform at the input that looks like this, the output will just be a square wave waveform, but it will be inverse of this, because in the next figure you notice that the input is given to the negative terminal and it's a positive which is grounded, which is the opposite of this. So be careful about that, because the output is always V2 minus V positive minus V negative, right? So in this case, the positive is grounded and the negative has the input. So the output is V positive minus V negative, and whatever is the input value, I will get the opposite of it at the output and the saturated value. Now when I have a feedback path over here, now that I have this R2 connected, let's take some example. Let's say the input were 5 volt. Supposing I'm applying 5 volts, then what will happen is V2 minus V1 is minus 5 volts. Let's assume initially, the system is just starting over here. Actually, it cannot be, minus 5 volts because it depends on the value of V out. So let's assume initially V out is also 0. So that makes it easy. So V out is grounded. This is at time, time step 1. So the positive terminal is grounded and initially V out is 0. If the input is 5 volts, then the difference of that is minus 5 because it's 0 minus 5, and therefore the output gets saturated to a negative value. Now because of this feedback path, what happens is the output voltage is going back to the input as a negative value. So initially I had a positive value at the input, and now due to the output I'm having a negative value, and that negative value is subtracting from the input value. Therefore the difference between these two terminals is reducing, right? So let's take the example that R1 is equal to R2. So let's say this is 1 kilo ohm, this is 1 kilo ohm, and if I have 5 volts over here initially, then you could say that if the output is 0, then the drop over here would be say 2.5 volts, because half of it is dropping across R1, half is across R2. Now I have 2.5 volts at terminal 1. The difference, the output will become 8 times minus 2.5, because V2 is 0 and V1 is at 2.5. So output is 8 times minus 2.5. So now it becomes a negative number. So let's say this goes to some minus saturation value. And therefore, once I've got like say minus 10 volts over here, then minus 10 will drop across this resistor path R1, R2. So I have 5 volts here, minus 10 here. So this can turn out to be something like minus 7.5. So essentially what was like a positive number is now getting subtracted, and this process can go on iteratively until the system saturates. And that's how this process of feedback is working. So whenever I have an input which is large, the output will try to suppress that input. Now remember that the input signal I'm applying, 5 volts over here, that is unaffected. That is coming from the supply source. It's this point over here, which I'll erase here. So the golden rule of the op-amp is saying that it does whatever is necessary to make the voltage difference between the inputs 0. Those inputs are referring to this point and this point. It's this terminal and this terminal. It's not talking about the parts over here, because there is a resistor segregating this. So what the op-amp is trying to do, the output, is to make these two terminals have equal voltages. And that's the main point here. So once I have like a voltage that, the feedback path, where I'll just erase all of this. So now if I have some feedback path, now what's going to happen is the output over here will try to make this difference 0. And since this is at ground, this has to come to 0. So if this has to come to 0, if this has to become 0, that means the output voltage should be minus 5 volts, right? Because then, since this is 1 kilo ohm, this is 1 kilo ohm, so this is an equal voltage drop. So if this is plus 5 and this is minus 5, this will be 0. That means the output of the op amp is floating to some voltage, which ensures that these two inputs have a zero difference between them. And therefore the output becomes -5, which works out with our formula that we derived last time, right? The output V out is equal to minus R2 by R1 times Vin. So that's precisely what's happening here. If R2 is 1 kilo ohm and R1 is 1 kilo ohm, then the output will become -5 volts. If supposing R2 were 10 kilo ohm instead of 1 kilo ohm,